So hello everyone, and welcome to another lecture uh, in the Transitions to Advanced Mathematics course. And so the last lecture was I uploaded the last lecture a little bit ago, and we finished our discussion about functions, and we ended on an interesting lecture on sequences. And now you might see that in the subsequent lecture I have this interesting number up here, 7, because we have skipped all the way forward to chapter 7. It's because I let you guys vote on which chapter you wanted me to cover, and the most votes went to chapter 7. And that is going to cover elements of analysis. And so analysis is a pretty important subject in mathematics. And the type of analysis that we'll talk about in this class is going to be sort of to give you sort of themes that come up in the study of real analysis. So like a rigorous study of real numbers and the properties therein. Okay, so and this is going to work really well, I think, because some of the elements that I talk about in this first section are going to be directly related to the things that we just covered in, for example, partial orderings and things like that. So it's a good section to jump right into. Okay, so today we're going to talk about the completeness of real numbers, and so a lot of times when we think about real numbers, most of us, when we think about real numbers, really tend to think about rational numbers, even though we know that irrational numbers are also real numbers. Um, but hopefully by the end of this section, what you all will see is that the real numbers, i.e. the rationals and the irrationals together, have some nice properties that rational numbers lack. And that's indeed what we call completeness. So let's get into what that actually means. But before that, we have to provide some structure to what we provide some structure, some more abstract definitions. And so, as is usual in many of these lectures, we're going to start off with the definition, because we're going to think about real numbers as what's called an ordered field. I have to define what I mean by this. So a field, which we usually denote with some letter and some binary operations. The field f, comma, plus, comma, dot is a set, okay, f, and this is an abstract set, okay, with two operations. And so even though I'm using the addition and multiplication operations to indicate what I'm doing, I haven't specified what the elements of f are. And so these could be any types of elements with any types of operations that can be that are combined according to some rule. And but the main things to think about are addition and multiplication of real numbers, such that we have the following properties. Okay, so plus is an operation on f such that for all x, y, z in that set, we have the following. Associativity of addition, which we know is going to work for the real numbers. So there exists an element 0 in f such that 0 plus x equals x plus 0, which equals x. And so this is the additive identity. For all elements in f, there exists a negative x in f such that x plus minus x equals minus x plus x equals the additive identity. So this is the inverse, additive inverse. And lastly, but not leastly, for this operation, we have that the operation is commutative, or abelian, if you want to be fancy schmancy. We're continuing the definition. It's kind of a long definition, but multiplication is an operation on F, so that for all x, y, z in F, we have that multiplication is associative, right? There exists there exists 1 in that set F, so 1 could be the real number, or it could be just representative of something that satisfies the next property, such that x times 1 equals 1 times x equals x. So this is multiplicative identity. For all x in the set, not including the additive inverse, there exists an element in F without the additive inverse, such that x times x inverse equals x inverse times x equals the multiplicative identity. And so this is multiplicative inverse. And lastly, we have that multiplication is also commutative. A third property is that multiplication is distributive over addition. So for all x, y, z in the set F, x times y plus z is equal to x times y plus x times z. And lastly but not leastly, we have that 0 does not equal 1. It's just a technical condition, but it is a condition that we need. And these are all characteristics that then we can call a set combined with two operations, however we may define them, to be a field. Okay? And again, the classical examples you should be thinking about are real numbers. Okay? And actually rational numbers work as well. So real numbers and rational numbers with standard addition and standard multiplication satisfy all these properties. And so the real numbers are a field, and the rational numbers are a field. Okay? Next, I'm going to give fields a little bit more order. And when I say order, I mean more structure, but I kind of slipped at the tongue because of what I'm trying to get at is the real numbers and the rational numbers are actually ordered fields. So let's define what that means. So a field F, so that means, F plus dot is ordered if and only if there is a relation strictly less than on F such that um, for all x, y, z in F, we have the following properties. So I've used this less than symbol to, again, sort of force you to think about these things, even though they are meant to be abstract in terms of real numbers and rational numbers. But it could be an abstract ordering. We talked about partial orders and orders in general in Chapter 3. This is just a very specific version of it. So what are the properties that make a field ordered is if the operation or the relation satisfies the following. X is not less than itself. Okay, so this is irreflexivity. Okay. It's also transitive. So if x is less than y and y is less than z, then x is less than z. Okay, so this is transitivity. This next one is kind of cool. Either, so I've given you two distinct elements. They must satisfy either x is less than y, x equals y, or x is bigger than y. That's true for any two rational numbers or real numbers. And this is called trichotomy, this property. If x is less than y, then x plus z is less than y plus z. Okay, that makes sense. And 5, if x is less than y and z is positive, then x times z is less than y times z. Okay, so all those properties, all those sort of defining characteristics I talked about on the previous previous page of notes, give you a field, and then if you can define a relation on that field that satisfies these 5 properties, you've actually constructed what's called an ordered field. Okay, and the standard examples of ordered fields are the real numbers and the rational numbers. So example, the real numbers with plus and multiplication is an ordered field. Same with the rational numbers. Now, ordered fields have really interesting properties because when we try to think about ordered fields, sometimes you think of an element, and then sometimes you think about what is the next element, right? If I say, oh, here's a number 0.1, and I say 0.1 is the element in a real number, sometimes we ask the question, well, what's the next real number? Well, or what's the next rational number, if we're talking about rational numbers? Well, these ordered fields have this very interesting property, and so I'm just going to list it with a star. And this property is that between any two distinct elements of an ordered field, there is a third element. So that's cool. Well, let's see why that is. So why? So let A, B, say, be real numbers with A less than B. And I want to prove that there's a number between A and B. Well, note, a plus a is going to be less than a plus b, and a plus b is going to be less than b plus b. That is, 2a is going to be less than a plus b. That's going to be less than 2b. Which tells me that between a and b, I have this number 1/2 a plus b. Okay, and you can do this for any set of numbers. So now let c equal 1/2 a plus b. You can do the same trick with a and c now. Or b and c now. So you can find numbers that are between a and 1/2 a plus b and 1/2 a plus b and b. And you can keep doing that. In fact, you can do it infinitely many times. You can implement this methodology infinitely many times, and you'll still have numbers you haven't discovered. And so this leads to another very interesting property. There are never any empty spaces between elements. So contrast this with integers, right? Integers, when we think of integers, we see them. We kind of see them as like discrete points on an infinite line. You cannot think of the real numbers as discrete points, or the rational numbers as discrete points. There's no space between them. There's no space between a rational number and the subsequent rational number. They just sort of form this continuum. And so yeah, there's no empty space between rational numbers. So let me just write down another interesting thing. Nowhere on the number line is there a number that is followed by the next real / rational number. That is, these ordered fields don't have the successor property that we talked about for natural numbers and integers. Okay. So yeah, so we established now what what it means for the rationals and the real numbers to be ordered fields. But as I said at the beginning of the lecture, I want to sort of eventually get to what special property the reals have that the rationals lack. And in order to do that, let's think about the following set. So I'm just going to do this as an example. This is sort of like an introductory lecture to sort of get you into the feel of things, but the idea of this analysis chapter is to get you really situated with what real numbers are and how to think about them and what kind of structure they have. So think of the following set. The set is all rational numbers such that x squared is less than 2. We know, okay, so we just look at this, and this is a simple quadratic inequality, so So all the elements of B satisfy B is less than the square root of 2, right? In particular, we can say that the square root of 2 is an upper bound for B. Um, you know, so square root of 2 is upper bound for B. I mean, there are infinitely many upper bounds, right? So if you think about partial orderings again, an upper bound is any number that's any element that's bigger than the ones in your set. And so with that general of a definition, square root of 2 might be an upper bound, but for example, um, so is 1.5, so is 2. And if you want to get closer and closer, 1.415 is an upper bound, 1.4143 is an upper bound, and numbers that are just bigger than the square root of 2 are all going to be the upper bound, and not the upper bound, an upper bound for this set. And you can try to get numbers that are closer and closer, and we want to find what is the supremum. We want to find the supremum, and we'd like to find, that is, we want to find sort of the smallest, we want to find the smallest number that's bigger, that's an upper bound for all of these, for all the elements in the set B. But in particular, we ask the question, can we find S in the rational numbers such that S equals the supremum of B? So can you find a rational number that is the supremum for this set? And it turns out, and we'll see shortly, no, we cannot find, spoiler alert, there is no rational number that is an upper bound for the set B here. And because the rational numbers is missing numbers like this, we say that the rational numbers are not complete. Yeah. Whereas the real numbers, as we'll see, is complete. So hopefully you all are comfortable with upper bounds, lower bounds, infimums, and supremums, but just to get you guys situated again, here's an example. In the ordered field R, infimum of this half-open interval equals 0, and the supremum of that same interval is 3. The infimum of the natural numbers is 1, and the supremum of the natural numbers does not exist, right? It's not bounded above. For A equal to powers of 2 inverted with k taken from the natural numbers. So in case you just want to see what this set looks like, you got 1/2, 1/4, um, sorry, yeah, 1/2, 1/4, 1/8, 1/16, dot, dot, dot. The infimum of A is 0 because these numbers are getting smaller and smaller with a lower bound of 0, but never getting past, they're never getting negative, but they are getting closer to 0. And the supremum of A is 1/2. For B being defined as it was just a second ago, x squared is less than 2. Infimum of B is the negative square root of 2, and supremum of B is square root of 2. In the ordered field, Q are the rational numbers. Infimum of A is 0, and supremum of A is still 1/2, so that's fine. But infimum of B, supremum of B do not exist in Q. And that's one of the main defining characteristics of a complete ordered field as opposed to an ordered field. That's one of the main differentiations between the real numbers and the rational numbers. Even though the rational numbers are dense and, in principle there's no space between them, you can still find these gaps. Okay. So we talked about supremum and infimum. Hopefully you're comfortable with those. If not, you can refer back to the notes on the partial orderings to sort of orient yourself as to what it means. The next theorem is going to give a better idea as to what a supremum actually tells you. So in particular, if I give you a set and you find a supremum for that set, everything that's bigger than that supremum is an upper bound for the set. And anything that's less than that supremum is not an upper bound for that set. Okay? And so we can make this precise with the following theorem. So let A be a subset of an ordered field F, then S is equal to the supremum of A if and only if the following two properties hold. For all epsilon greater than 0, so no matter what positive number you take, if x is an element of A, then x is less than s plus epsilon. So no matter how small you take epsilon, if you add that small increment to the supremum, that increment is going to give you an upper bound for the set. And secondly, for all epsilon bigger than 0, there exists a y in that set A such that y is bigger than s minus epsilon. So this is an interesting one because no matter how small you take epsilon, you can take epsilon to be arbitrarily small. if you take away that small amount from the supremum, you're going to find an element in that set which is bigger than that decreased amount. So it's pretty cool. Okay. So let's prove this. So this is a biconditional statement, so we have to prove both sides. So first, assume S is equal to the supremum of this set A. Okay. Let epsilon, positive epsilon, be given. So these types of statements are sort of universal in analysis proof. So we saw this when we were doing sequences as well. Yeah. Then for all x in A, x is less than or equal to S, okay, by definition of supremum, and just by ordered, just because the field F is ordered, that's going to be less than S plus epsilon. So part 1 is done. For part 2, suppose epsilon greater than 0 is given. And no y in A exists such that y is bigger than S minus epsilon. Then S minus epsilon is an upper bound for A, which is a contradiction, since S equals the supremum of A, the least upper bound. Okay. So we proved that if you have S as the supremum of A, then properties 1 and 2 follow. Now we have to prove the other way. So now, suppose S satisfies one and two. We first show that S is an upper bound for A. That seems like a reasonable first step because, to show it's a supremum, you have to first show it's an upper bound for this set. That's a good place to start. So suppose there exists a y in A with y bigger than S. If we let, sorry, not y, if we let epsilon equal y minus s divided by 2, then y is bigger than s plus epsilon, which violates condition 1. So the way we chose this epsilon is to basically illustrate this contradiction we get if we assume that there's an element of y that's bigger than s. So we just chose this, and actually if you just solve for y in this equation, epsilon equals y minus s divided by 2, you get that y is what? You get that y is 2 epsilon plus s, which means y is bigger than s plus epsilon. And because by condition 1, y must be less than s plus epsilon for any epsilon, that's a contradiction. So y is less than or equal to s for all y in A. Okay, we're not quite done with the proof yet, because you have to show that, now you have to show S is the least upper bound. Now, need to show S is least upper bound. Suppose there is another upper bound, T, such that T is less than S. If epsilon equals S minus T, then by condition 2, there exists a z in A such that z is bigger than s minus epsilon, right? Which equals s minus t, which equals t. So t is not an upper bound for A. Therefore, S equals the supremum of A. Okay. So, okay, let's see this in action. So, example. In field R, consider the open interval 2, 4. The supremum of 2, 4 is 4. Okay. And take epsilon equal to 0.00001, right? So for all x and 2, 4, x is less than 4 plus epsilon, which is 4.00001. Okay, that's true. And if you take what is 4 minus epsilon, which is what, 3.99999, something like this. This is not the supremum. This is not an upper bound for the interval 2 to 4. You can actually find infinitely many real numbers between 3.99999 and 4. And so you can take epsilon even smaller and try the same trick, and you'll still fail in the same regard. So this is just an example of the theorem in action. Sorry, I just need to take a sip of water. Okay, so now we're going to get to the meaty example of the chapter. Sorry. So as we said, the rational numbers are missing some numbers. In particular, that set that we were talking about, B, from before, which is the rational numbers whose squares are less than 2, we're going to prove that the supremum of that and the infimum of that are not in the rational numbers. And to do that, we're going to use the Archimedean principle. And I've talked about this before in class, but so for every positive real number R, there's a natural number K such that 1 over K is less than R. No matter how small you take R, I can find a natural number whose inverse is less than that real number. Okay? So now let's get to this meaty example. The set B, which is the set of rational numbers, such that x squared is less than 2, is bounded above in the field Q, but has no supremum. In the rational numbers. So let's prove it. Proving the first part is easy. It's bounded above in the field Q. So, for example, 3 is an upper bound. For B, and 3 is an element of the rational numbers. And that proves that it's bounded above in the field, the rational numbers. In fact, you can find infinitely many rational numbers that are upper bounds for the set B. So B is bounded above in Q. Now suppose S is a rational number and S equals the supremum of B. We will show that both S less than square root of 2 and S is greater than square root of 2 are both false statements. So we're going to show that both of these statements are false. If s is less than the square root of 2, then the square root of 2 minus s is positive. Okay? So let k be a natural number such that 1 over k is less than square root of 2 minus s. Then s plus 1 over k is less than the square root of 2. Yeah. And s plus 1 over k is rational. So s plus 1 over k is in B. And this is a contradiction because S is the supremum of B, and we just talked about that other theorem we talked about, where if I take the supremum and I add some small increment to it, all the elements of B should be less than that slightly incremented supremum. But here, I've taken the supremum, I've added a small increment to it, and it's still in this set. And from last theorem, this cannot happen. If s is bigger than the square root of 2, then s minus square root of 2 is positive. Let m be a natural number. So again, this is from the Archimedean principle, such that 1 over m is less than s minus square root of 2. Then s minus 1 over m is s minus 1 over m is bigger than the square root of 2. And s minus 1 over m is rational. So for all x and b, we have x is less than square root of 2. But now we've shown that that's less than s minus 1 over m, which is less than s. So in fact, we found a smaller upper bound. So that's a contradiction, because s is the supremum. So s bigger than square root of 2 is false, and s less than square root of 2 is false. So s equals the square root of 2 and is not an element of Q. So the supremum of the set B is not an element of Q. So again, this is an interesting result because the rational numbers have no gap, right? The rational numbers have no gaps in them, but they kind of have these pinholes. Yeah, it's kind of interesting. One thing to note here is that I've talked about supremum a lot, but the entire thing stands for infimum as well. You could have done the same proof for the infimum as well. So now let's finally go on to a definition of what I mean by a complete set. An ordered field F is complete if and only if every non-empty subset of F if every non-empty subset of F that has an upper bound in F has a supremum in F. Yep, so that's what that means, and notice that this fails for the rational numbers by the previous example. This does not fail for the real numbers. So that's the theorem. The field R plus with multiplication is a complete ordered field. All right. So hopefully that gave you a good taste as to why the real numbers are so much cooler than the rational numbers. And this actually gives a nice, actually this gives really nice properties to real numbers as compared to rational numbers. And yeah, so that concludes this section. I hope you enjoyed it. I hope you're interested in continuing your march through analysis because it is the bomb. All right, so I'll see you in my next lecture. Thanks for listening.